Good evening, everyone. Let's start the program. Prayer is a window to opportunity, a door to miracles, a channel for blessings, and a path to dreams come true. With that said, let's ascend for the prayer song.
நீராறும் கடலுடுத்த நிலமடந்தை கெடியொழுகும் நீராறும் மதனம் நிகழ்வத கண்டறிந்து எக்கணமும் அதில் சிறந்த நாகிழவன் திருநாளும் தக்க சிறு திரை முதலும் தரித்தனரும் திலகமுமே திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே முன் சீரிழமை திகழ்ந்து செயல்படுந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
An anthem is rousing and reverential that represents the ideals of the group of people. Now, let's harmonize our college anthem.
இங்கேதான் அன்பு கிடைத்தது பண்பு கிடைத்தது நட்பு கிடைத்தது கனவு கிடைத்தது நம்மீஸ்வர் கல்லூரி இங்கேதான் தெளிவு கிடைத்தது அறிவு கிடைத்தது அறவு கிடைத்தது அனைத்தும் கிடைத்தது நம்மீஸ்வர் கல்லூரி பசுமை வண்ணம் கொண்ட சூழலிலே மயில் கொண்ட கல்லூரியே ஒற்றுமைக்கும் தேசிய கொடியும் ஆசிரியர்கள் எல்லோரும் வெற்றிகள் அஸ்திவாரம் ஆதரவு இல்லாமல் விடிகள் ஏது பாதைகள் இல்லாமல் பயணம் ஏது கேள்விகள் இல்லாமல் விடைகள் ஏது ஈஸ்வர் கல்லூரி இல்லாமல் இன்பம் ஏது. Community center. அங்கே உலகம் கற்றுக்கொள்வோமே நம் காலேஜ் பிளேஸ்மெண்ட் அது என்றும் சூப்பர் அங்கே வேலையும் பெற்றுக்கொள்வோமே 4 ஆண்டுகளே என்றாலும் ஒரு குடும்பம் போல வாழ்ந்திடுவோம் 40 ஆண்டுகள் கடந்த பின்னும் நம் கல்லூரி நாட்களை போற்றிடுவோம் நிலையை நாங்கள் அடைந்தாலும் வாழ்வில் உயர பறந்தாலும் மரபோம் ஒரு நாளும் மகள் ஈஸ்வருக்கு இந்த நாட்களை ஈஸ்வர் கல்லூரி வாழ்க்கை கற்று தந்த பாடம் காலம் கண்ணில் நிழலாடும் ஆதரவு இல்லாமல் விடிகள் ஏதோ பாதைகள் இல்லாமல் பயணம் ஏது கேள்விகள் இல்லாமல் விடைகள் ஏது ஈஸ்வர் கல்லூரி இல்லாமல் இன்பம் ஏது.
Anyone can steer the ship, but it takes a leader to chart the course. We are delighted to heartily welcome the captain of our ship, Dr. R. Suresh, head of the Department, Science and Humanities, to deliver the welcome address.
Honorable Chief Guest, respected Chairman, respected Director, respected Principal, Dean Research and Innovations, Dean Industry and International Relations, Dean Academics, heads of various departments, and all the valued participants. A very good evening to all. On this wonderful occasion, I feel I feel happy and on this wonderful occasion, I feel happy and privileged to welcome you all for the 2-week blended FDP on radiation exposure and its impact on human health, sponsored by AICT Training and Learning Academy and organized by the Department of Science and Humanities, Sri Ishwa College of Engineering. Indeed, it is a great honor for all of us to have in our midst Dr. B.R. Kerur, Professor and Chairman, Department of Studies and Physics, Gulbarga University, Karnataka. He is a scholar, person of eminence, and known for his wonderful administration and high achievements. Notwithstanding his demanding schedule, he gladly accepted our invitation to be the chief guest for this online inaugural function to inaugurate and to deliver the keynote address. We feel honored in offering him a cheerful welcome. We welcome you, sir. We extend a warm welcome to our beloved and respected chairman, Sri Mohan Ram sir, respected director, Sri Rajaram sir, and respected principal, Dr. Sudha Mohan Ram madam, who always care for the benefit of the student and staff community and for being the source of energy within us to realize the best version of ourselves. Our sincere welcome to the management team of Sri Ishwa College of Engineering. A man of just with a quest for the best, his vision and guidance leads us towards success. The ever-charming Dr. Karupasamy, Dean, Research and Innovations, we welcome you, sir, for presiding over the function. We extend a warm welcome to our Dean, Industry and International Relations, Dean Academics, heads of various departments. The sincere and tireless efforts by the coordinators and co-coordinators of this event is highly appreciated, and our laudable congratulations to the entire team. We are delighted to offer a happy welcome to the coordinator, Dr. Krishnamurthy, Associate Professor, Department of Physics, and the co-coordinators, Dr. Sangeeta and Dr. Selvakumar, Associate Professors, Department of Physics. Our sincere welcome to all the valued participants, and we send good wishes and effective learning to all to make this event and program a meaningful and successful one. Once again, we welcome you all for this inaugural function. Thank you.
Thank you, sir, for your evaluated speech that made us bounded. Now, we invite Dr. N. Krishnamurthy, Associate Professor, Department of Physics and ATAL FDP Coordinator, to give away the program address.
Good evening, one and all. Raising the virtual inauguration of the ATAL-sponsored 2 weeks blended faculty development program on radiation exposure and its impact on human health. Before I could give a short note on this FDP, I would like to thank my chairman, sir, director, sir, principal, madam, my HOD and HODs of various departments, our deans, and our staff for their encouragement and support in organizing this FDP. Special thanks to all the ATAL officials for accepting our proposal and for sponsoring this FDP. The FDP is conducted both via virtual mode and offline mode with a total of 33 sessions. And these sessions will be organized by 14 experts in the relevant field. The experts will be sharing their knowledge in all fields of their expertise. This FDP will substantially progress the furthering knowledge about the ionizing radiation, its assessment, hazard, safety, radiation protection, and the application in our day-to-day living. This program is also interested to review and discuss recent achievements in radio ecology, environmental radioactivity, and related disciplines, as well as to promote continued development in these subjects in order to improve the radiological protection of humans and environment. The objective of the FDP is to increase the public's knowledge on the benefits and risks associated with radiation, current and future radiation related issues, its development and application of radiation protection. This program aims to serve as a platform for faculty members to interact on all aspects of radiation concerned to human health and nature. Thank you.
It's a honor and prerogative happiness to have our Dean, Research and Innovation, Dr. Karpusamy sir, who has always been a person of inspiration to every individual up here to inculcate development in their thoughts. I request you, sir, to give the presidential address.
Oh, thank you very much. Good evening to all of you. You are able to hear me?
Yes, sir.
You are able to hear me?
Yes, sir.
Yes, sir.
Okay, thank you. Thank you very much. Happy to note that the Department of Science and Humanities, headed by Dr. R. Suresh, and the coordinator, Dr. Krishnamurthy, co-coordinator, Dr. Sangeeta Madam, and Dr. Selva Kumar, and the entire team of Science and Humanities is organizing a 2 weeks FTP, ATAL FTP, on the topic radiation exposure and its impact on human health. Definitely, this is a highly interesting topic. And I hope all the participants who are going to attend this online program for a week and offline program for a week will definitely benefit out of this FTP. The reason is, you know, the radiology or the radiation, the technique was invented as early as 1895 by a German scientist, Röntgen. 1895. For the last 130 years, close to 130 years, so much of development. Radiation, you know, the technology is used positively as well as negatively. And I hope this FTP will concentrate on the positive aspects of radiology or radiation. Take the field of medical. Medical field, you cannot imagine without radiology, the Department of Radiology. So much of useful applications of radiology. Same way in engineering field, for example, I am in mechanical engineering. We also use radiation. Definitely the concept is called non-destructive testing. You know, let us say we do a welding of a joint welding. If I want to see the porosity inside the joint, it is not possible with eyes. Open eyes, you cannot see that. We use X-rays to detect the porosity of the weld. In other words, a lot of industrial applications of the radiation as well as medical applications. In fact, the degrees offered in radiology is really huge. You know, the doctors can do MBBS and then they can do MD in radiology. And parallelly, a lot of technician jobs are also available in radiology. So medical field, we cannot imagine without radiation. And I have gone through the brochure of the FTP, radiation exposure and its impact on human health. I think they are trying to cover almost all the aspects of radiation. It's a wonderful beginning, and we really thank AICTE for sanctioning this FTP program for our college. And definitely I'm seeing the Science and Humanities Department headed by Dr. Suresh. They are doing a wonderful job. In fact, morning until now, it looks to me they are still in the college. Morning until now, morning we had the inauguration of the first year students. And in fact, they worked yesterday, day before yesterday. Continuously, the first year department is working for the last 1 week without a break. And this FTP also they have organized so nicely. I have seen all the preparations they have done, especially the resource they have arranged, including the chief guest and the keynote speaker today, who is going to talk on the topic, Dr. B. Kerur sir, professor and the chairman, Department of Studies and Physics, Gulbarga University, Karnataka. We are really happy to have you on board, sir. Definitely, you will add so much of weightage to the program, and the input you give to our participants will definitely benefit them. So with this small note on the radiation exposure FTP, I thank all the organizers. I congratulate all the organizers for organizing this program. Definitely it is going to be useful for all the participants. Thank you very much. Thanks for the opportunity given to me. Over to the MOC.
Thank you, sir.
You have showed us what an eminent leader is. Thank you, sir. I am profoundly delighted to take an opportunity to introduce the guest of honor for the day, Dr. B.R. Kerul, Professor and Chairman, Department of Studies and Physics, Gulbarga University, Karnataka. He has about 30 years of experience in teaching. His research interest lies in the area of radiation physics. He has an administrative experience as controller of examination at Central University of Karnataka and successfully conducted 4th, 5th, and 6th convocations at Central University of Karnataka. And he was registrar in charge at Central University of Karnataka on different occasions. He has been awarded as Young Scientist from Karnataka Associate in the year 1997 and elected member at Institute of Physics, London, elected member of Executive Body at Indian Association of Radiation Protection. It's a pleasure to have you, sir.
Basuraj sir.
Sir, is this audible?
Professor Kerul.
Sir?
Professor Kerul.
Hello, good afternoon, good evening. Am I audible?
Yes, sir, you're audible.
Yeah, please. Yeah. Okay, sir. Our session will start now.
Yes, sir.
Yes, sir.
Okay. Thank you, sir. Good evening to one and all. Today's president of the today's function, the head of the department, Parani Swami. Head of the department of the radiation physics, Raman, and Dr. Dr. N. Krishnamurthy, and other members of the department. I'm happy to here to be present for the inauguration of this session, Dr. N. Krishnamurthy, and also I thank the Dean Ramesh, I think, and all physics department and all teaching and non-teaching staff of this department. There is a lot of work is going on in radiation, in the sense radiation physics, especially Puja, especially radiation is a very, very important aspect in our daily life. The faculty develop in that sense, the faculty development program that is usually conducted to spread knowledge in the emerging thrust areas such as the radiation or science and technology and other thrust areas like food science. So thrust area, there are different thrust areas. Among one is the emerging thrust area is also radiation. And these thrust areas should give an importance to the value-added courses. And after learning, they have to have a field employability. That means after learning something, they have to have a employment. That means on their own, they can earn money. And the focus should be on the applications based thrust areas like radiation, environment, food, science and technology, or health sciences. And the involvement in the project management by the creative thinking and spreading the knowledge to all the publics. That means whosoever is coming out from the from a diploma or a certificate course or a degree course or a master degree course, he should be in a position creative thinking and spreading the knowledge to all. So usually, usually village people have had a creative thinking, and they are having a very sound knowledge on the subject, but are unable to communicate to all the people. So this gap has to be filled between the learned persons. That means there are persons who don't know about the creative thinking, and the village people who knows about communication. So this gap has to be filled. So hello, I'm audible.
Yes, sir, you are audible, sir. You
Oh,
can.
okay, okay. So the organization has said me about the brochure and program schedule, the topic in which this ATL FDP faculty development program is to be conducted in a very appropriate time, and it's also very precious one, and that is required to day-to-day life. We all know radiation is present everywhere. That means the sense if you drink a water, there radiation is there. If you eat anything, any food material, radiation is there. However small, that radiation is everywhere. If you take the earth atmosphere, radiation is there. If you go to the outside the sphere, there also radiation is there. And if you go to space, there also the radiation is there. Or if you go to any space, radiation. Without radiation, nothing is exist on this universe. So radiation is part of our life. However small, radiation is always there. It may be a very microminute level, or it may be very high level. So we have conducted radiation survey of this region. That means north east Karnataka region. Now it is called as the Karnataka region, of the samples, like water samples we have studied, granite samples we have studied, soil samples we have studied, and other food materials we have studied. So like that, we have found there is a large variation from one space to another space. And I'm happy to say that Dr. Krishnamurthy has sent some samples. So such samples also we have analyzed on the different context. So we have published research papers in that regard. So radiation is playing a very, very important role, be it in science and technology, or be it in environment, or be it in a aerodynamic engineering, or it is mechanical engineering, or the medicine, or you can say it is a food radiation and all that. And in the energy sector, that means radiation can be used in a very peaceful manner, like the nuclear radiation, that the nuclear reactors. The nuclear reactors are producing the nuclear energy, where the nuclear radiation reaction is going on, and that radiation we are using in a systematic manner. So if you use the radiation in a controlled manner, then that is called as a nuclear reactor. So, and that whatever the heat is, excess heat is generated, that will be taken off through the thermal energy, and then from thermal energy, the D's will exhaust, in the sense that D's will rotate in the magnetic field, electric and magnetic field. So electricity is generated. Radiation is also used to cure the cancer samples. Radiation is also used to irradiate our syringes to kill all the bacteria, viruses. Radiation is also used to food irradiation. Let us say if the food is going from one place, that means let us say from Coimbatore to America. So the radiation, because if you send the food articles like that, the food articles will die, in the sense they will spoil in between through the sea or through the air. So what they do is they will irradiate all these food samples depending upon the whether it is a mango, whether it is a green chili, or it is a other food materials, or if it is a seeds, or if it is a dry fruits. So all these dry foods are irradiated according to the consumption. That means how much radiation is to be irradiated. That is usually calculated through a earlier, that is through some mechanism. So what the kind of food to be irradiated for different kind of food materials is also known. It has been done through the Indian Nuclear Society, and is also been covered. That means governed by the International Atomic Energy, and also there's our AERB, Atomic Energy Regulation Board. So these two bodies are governing the radiation to be exposed to the food materials, and radiation also used to see or to check the cracks in the gas pipelines, like if a gas is to be uploaded to the auto rickshaws. So there, if there is small hair crack is there, then there will be a okay. Now it's okay, sir. Yeah. Hello. Yeah, the without radiation, human existence has doesn't any value. So radiation is playing very important role in our daily life. Now, because the organizer has this, I think ATL, ATAL, FDP. That means it's playing very important role. Last time also they conducted one seminar about for a week time. This time also they are conducting FDP program for the benefit of the public as well as the college teachers, so that the radiation knowledge about the radiation has to be spread throughout India, and from the higher level to the even grassroots level, like village people, so that we can have a very good exposure to the radiation. And we can because once if you say radiation is there, we find that we frighten. So that frightenness has to be go. It's because such seminars or such programs are to be conducted at a very regular manner. So in this regard, I thank the management, the principal, dean, HOD of Science and Humanity, and program coordinator and co-coordinator of this program, and organizing committee members for giving me the opportunity to inaugurate the ATAL sponsored faculty development program through this virtual mode, and to deliver the keynote address. Thank you.
Your kind presence in the program encouraged us a lot. Thank you, sir, for sharing your expertise. Every incident attains its perfection with gratitude. Now, I request Dr. B. Selvakumar, Associate Professor, Department of Physics, to deliver the vote of thanks.
Thank you. Gratitude is not a word of the words, but in the heart which expresses it. Indeed, it is a great honor and privilege to propose the vote of thanks on this occasion. First and foremost, I express my sincere gratitude to our chief guest, Professor B.R. Karur, who, despite his busy schedule, has found time to grace this event. My heartfelt thanks to our chairman, director, and principal madam for always encouraging and supporting us to participate and learn more. Sincere thanks to our head of the department, Dr. Suresh, IT Dean, Dean R&I, Dean Academics, and who guided and supported us whenever we approached. We owe our special gratitude and credits to all the heads of various departments, the faculty coordinators, and the office bearers for making this inaugural function a resounding success. A wide round of applause and thanks to all the participants who made the event a memorable one. Finally, I would like to thank all of you present here for making the time to be with us today and helping us to make this event a grand success. I would be failing in my duty If I did not thanks my fellow students, Media Max team, admin team, who had made this day possible. I would also like to thank each and every one of you for being here and make this day a wonderful and memorable one of our dream teachers. Thank you once again. Last but not the least, I thank the coordinator and the organized team and all my fellow mates for insisting your presence here. Hope you all got some motivation and useful information to move forward in your journeys. Thank you, everyone. Finally, I'd like to thank Almighty for blessing me today and helping us to make this event a grand success. Thank you all.
That was an absolute package of gratitude. Thank you, sir. Now, let me introduce Dr. G. Shanti, Professor, Department of Physics in Women's Christian College, Nagarkoil since 1990. She did her research in radiation physics and awarded PhD in year 2010. During her research work, she presented a paper in University of Australia. She is a member in various professional bodies related to radiation physics. She is approved guide in MS University, Tirunelveli. 8 scholars completed their PhD under her guidance, and 4 more are currently undergoing research. She has published many papers in international journals. We welcome you, ma'am.
Yes, ma'am.
Yeah. So good evening to you all. I'm very happy that Sri Ishwara College is conducting an ATAL program. Then the ATAL is sponsoring a 2-week blended faculty development program on radiation exposure and its impact on human health. I'm very happy that it is a social relevance topic of the day. Now I take this opportunity to thank the organizing committee members who have invited me for this great platform to deliver a talk on interaction and detection of radiation. My sincere thanks are due to the authorities of the college and the Department of Physics. And my special thanks to Dr. Krishnamurthy, who got my willingness before some 3-4 months back. And from that, immediately after getting this, the willingness of the proposal is got sanctioned, Krishnamurthy contacted me, and I'm very happy and congratulate all the organizing committee to get such a fruitful event from the ATAL to conduct a program for the faculty development. And let me congratulate all the organizing committee members and the college authorities. And I was overwhelmed when I was watching this your college song, where the Krishnamurthy was sharing this. It's a wonderful college. Thank you so much for your wonderful this song and this college sceneries at all. Now, my best wishes to all the participants for getting this chance to complete a FDP program with this ATAL. Now I thank actually this ATAL, the organizer, the authorities to give a sanction to sanction such a nice program. For actually from Krishnamurthy, I came to know that nearly 300 or 350 people, the colleges have applied, and only 20 or 30 colleges have got such a wonderful opportunity. So once again, let me congratulate all the authorities and my best wishes for all the participants. So now we are going for this session. The session we are going to have is the interaction and detection of radiation. Am I audible to you all?
Yes, ma'am.
Yes. Okay. Okay. Now, the topic to be discussed in this session is what is radiation, types of radiation, interaction of radiation, why to detect radiation, and how to detect radiation. Now, what is meant by radiation? The word radiation was used until 1900 to describe the electromagnetic waves. After the discovery of electrons, the X-rays, and natural radiations, these were included under the term radiations. Am I audible? Am I audible?
Yes, ma'am.
Am I visible?
Yes, ma'am.
Am I visible to you all?
Yes, ma'am, the screen is visible.
Very good. Okay, okay. What is nuclear radiation? When an unstable nucleus tries to attain a stability by emitting a high-speed charged particles or electromagnetic waves, radiation can come from many sources, both natural and man-made. So from this word, so I came to know from Krishnamurthy sir that many people you are coming from, you are actually majority you are from the science faculty and you are from the physics and chemistry departments. So you know what is unstable nucleus. Am I clear to you? Am I audible to you? Am I audible to you?
Yes, ma'am.
Some noise is coming. No problem. Okay, okay, okay. So the participants, you know what is unstable nucleus. So unstable nucleus, or this the nucleus, the radioactive nucleus. Normally we say it is an unstable nucleus. So this unstable nucleus will not be there in this unstable state for a long time. So it tries to come to the stability by adjusting something and by emitting some radiation. So these radiations, the radiations are coming from this unstable nucleus. On the way, when they're trying to come to the stability. So this radiation is a form of energy. It can come from unstable atoms. So there are two kinds of radiations. One is ionizing radiation and another one is non-ionizing radiation. So this ionizing radiation also, you know what is ionizing radiation means? If an radiation falls on a matter, the matter gets ions. You know the matter. Normally, the matter consists of atoms and molecules. So you know the atom is neutral. The molecules are neutral. So if a radiation comes and hits this atom, the uncharged particle, the uncharged matter becomes charged one. So that is called as ionizing radiation. So the radiation that can form ions are called ionizing radiations. Now, source and modes of radiation. The sources of radiations are cosmic radiation, terrestrial radiation, anthropogenic radiation, and the modes of radiation are alpha ray, alpha decay, beta decay, and gamma ray emissions. Now, as I told you, on the way of this instability to the stability, the unstable nucleus tries to come to the stable nucleus. It is emitting some particles. So the important rays we are dealing, or we can see the category in this nuclear radiations are alpha rays, beta rays, and gamma rays. Okay. So this alpha rays is nothing but when a nucleus emits an alpha particle. So what happened is, so the example given here is, any problem there?
No, ma'am. You can continue, ma'am.
Hello? Hello?
Yes, ma'am, you can continue, ma'am.
Okay. So some noise is coming, that's why I was wondering. Okay, so when a nucleus emits an alpha particle, so I am here, the given an example given here is uranium. So uranium-92-235 is a radioactive material. So this uranium-92-235 is an unstable nucleus. So this unstable nucleus is trying to come to stability. So in one time, it is emitting an alpha particle. Actually, it won't emit an alpha particle always. So it, in a particular instant, if it emits an alpha particle, so this uranium is transmuted into thorium. So this alpha particle is nothing but a helium nucleus. You know, the helium nucleus, we normally call it as a doubly ionized helium atom or helium nucleus. So He24 is a nucleus. So this nucleus, we call it as alpha particles. Now, when a nucleus emits a beta particle, what happens? So the beta particles means, you know, that is beta particles is how the beta particles comes is a neutron is converting into a proton. Your neutron is converting into a proton. Actually, when it's unstability nucleus is tried to come to the stability in lot of ways. So one of the ways is to emit alpha particle, or these two protons and two neutrons, and another way is to convert a neutron to proton. So you see, when a neutron is converted into proton, so here the thorium And when after emitting this electron, what happens? You are getting a protactinium. So its atomic number becomes 91. So you people, you know, that's the left hand side, it is 90, and the right hand side is 91 minus 1. So this conversion of this neutron to proton, you are getting an electron. So that electron, we call it as a beta particle. And next is gamma rays. Gamma rays, so that is some particles on the way, it will become some exciting particles. So these exciting particles, you know, it will not be there in the excited state for a long time. So it emits, that's from the higher energy to the lower energy, it tries to come to this lower energy. So by emitting photons, so that photons are called as gamma particles. Now, the place of the nuclear rays. So the place in the spectrum. So this non-ionizing radiation is nothing but an electromagnetic radiation with wavelength lambda of about 10 nanometer or longer. So that part of the spectrum includes radio waves, microwaves, visible rays, and ultraviolet rays. And the ionizing radiation includes the rest of the spectrum. So this now our spectrum is categorized as two, that is non-ionizing and ionizing. So in this non-ionizing, it comes, and the non-ionizing, it comes this microwaves, radio waves, visible rays, ultraviolet rays, and all. And the ionizing radiation, it comes this X-rays, gamma rays, and all. Now we are going to see the properties of nucleus. So what are the properties of nucleus? The properties of alpha rays. So the radioactive emissions, we are getting 3 rays. What are they? Alpha, beta, and gamma. So the alpha particle is nothing but a helium nucleus. It consists of 2 protons and 2 neutrons, and it carries 2 units of positive charge. So this 2 positive charge comes from 2 protons, because you know neutron has no charge. Hello, am I audible? Am I clear to you?
Yes, ma'am, you're audible.
Participants, are you okay with me? Participants, are you okay with me?
Yes, yeah, we are okay with you, ma'am.
Yes, okay. If sometimes my flow will, speed will increase, please break me, but give a break, okay? Okay, so this is, okay. So here
Okay,
the particles are helium nucleus consisting of 2 protons and 2 neutrons. And it carries 2 units of positive charge. And since the alpha particles are charged particles, they are deflected by electric and magnetic fields. And the direction of deflection shows that they are positively charged particles. Actually, since it is of charged particles, it automatically will be deflected by electric and magnetic field. And they produce the fluorescence. So fluorescence, just like when the alpha rays falling on a fluorescent substances, that is the zinc sulfide or barium platinocyanide, your fluorescence we can see this fluorescence, and this fluorescence can be observed through a low power microscope. Now, when the alpha rays pass through, they can ionize the gas. So, you know, these alpha particles are very pretty particles. It has 2 positive charges. So these 2 positive charges, when it passes through a matter, what happens? It tries to attract the nearby electrons. Some free electrons it will attract. So what happens? They ionize the gas through which they pass. So the ionizing power is very much greater than beta rays and gamma rays. So it's numerically it is given like this. So this ionizing power of alpha particle is 100 times greater than of beta rays and 10,000 times greater than that of gamma rays. And they can be easily absorbed by metals, because you know why is it? The ionizing power is very high. So on the way, when it hit a particular substance, what happens? It will be ionized. So the alpha rays, its property diminishes. It's the property, losing its property. Because immediately after nucleus, it hits a matter, what happens? It becomes an helium atom. So we cannot, when it becomes a helium atom, we cannot say it is an alpha particle. So it becomes an helium atom. Okay, so that's why it says they are easily absorbed by thin metal foils or even by a small sheet of paper. The next is the properties of beta rays. So the beta particles possesses a negative charge because in the transmutation equations, we saw the beta particles are nothing but electron, E -1, 0. So the beta particle possesses negative charge and mass which is equal to that of electron. So the beta particle is fast moving electron because the beta particles, why it is fast moving means the beta particles, the weight is the light weight of electron. And the weight of helium, the helium nucleus, the helium consists of 2 protons and 2 neutrons. So the proton mass is nearly the electron mass is nearly 1,000 times lesser than 100,000 times greater than the mass of electrons. Actually, the proton mass is almost 1,000 times greater than the mass of electron. So the nucleus is very big in size when comparing the electron. So the lighter particle can move very fast comparing with this alpha particle. And the beta particle, since it has this charge, it is also deflected by electric and magnetic field. And it also causes this fluorescence when it falling on this fluorescence materials. And the ionizing, they also can ionize because this electron is a fast moving electron. It is also having a negative charge. So this negative charge, what happens? It is going and hitting an atom. It is going and taking a place in this atomic, the shells and all. Then what happens? This atom now becomes a negative ion. So when an atom, when an atom gains an electron, what happens? The atom now becomes a negative ion. Now the penetrating power is 100 times greater than that of alpha rays. Because in the alpha rays we saw the ionizing power is 100 times greater than that of beta. The alpha's ionizing power is 100 times that of beta. So here we can say the penetrating power is 100 times greater than that of alpha rays. Now the properties of gamma rays. Gamma rays are electromagnetic radiations of very short wavelength, and they're not deflected by electric and magnetic field, and they ionize the gas through which they pass because the ionizing power is very small because it has no charge since it is moving with the velocity of light. So with that, sometimes it may hit the outermost electrons of this atom and the atom now becomes ions. So but ionizing power is 100 times lesser than beta particles or 10,000 times lesser than alpha particles. But we can see the range of gamma particles are very higher comparing with the range of alpha and beta. So what is the range means? As I told you in this alpha particle, the alpha particle is traveling through the distance traveled by the alpha particle or the helium nucleus as a helium nucleus. Immediately if it attracts with an electron or anything, so that loses its identity as nucleus, it becomes an atom. So the distance traveled, that is called as range. So here the range of alpha particle is very less, but when the range of gamma particles are very greater. Now we are coming to the topic, that is interaction of radiation with matter. So there are, we saw there are important types of radiations are alpha, beta, gamma. So this in this picture, the right-hand side picture, we can see the alpha particles are deflected towards the left-hand side, that is towards this negative electrodes, and the gamma beta particles are deflected towards this positive plate, and the gamma particles are undeflected particles. So here this alpha particles are deflected towards the negative side and beta particles are deflected towards the positive side. This says that beta particles are negative particles. So here we can say in the second right-hand side, the second diagram, you can see the alpha particles, the range of alpha particle is given. So the alpha particles are moving through the small thin paper or a skin, and beta particles are stopped by aluminum plate, and gamma particles can be stopped by a dense materials. Now the absorption coefficient. Gamma and X-rays, which are both electromagnetic radiations, have no definite range because we cannot say, because it will go till there is an dense material, it will go. Okay, so a well-collimated gamma rays show the exponential absorption in matter. So just like this, your X-rays, this alpha particles are also, hello? Any problem? Hello? Hello, sir?
Madam, no problem. You can continue, ma'am.
Okay, sir. Okay, sir. Am I audible? Am I audible and visible by screen?
Yes, ma'am, it's audible, ma'am.
Yes, yes. Okay, okay.
The screen is also visible, ma'am.
Okay, okay, okay. So yes, just like this X-rays, this electromagnetic wave, it is also absorbed by the material. So here this absorption layer, so this the intensity of absorption is proportional to this thickness, and the intensity of this, how much intensity is absorbed depends on this the characteristic property of the material, that is called this absorption coefficient. And also, so we can say this intensity of this gamma rays after traveling through a distance. X is equal to I0 into e power minus mu x. So our mu is called the constant of proportionality, and this mu is, in other words, it's called that's an attenuation coefficient, or we can call it as an absorption coefficient. Now, the types of interaction with matter. So when this normally this types of interaction with matter is happening with gamma rays, because why is the alpha and beta, they are charged particles, and when it enters into this material medium, immediately it will be lose its identity. Alpha particle become, that's the helium nucleus, now becomes helium atom, or this electron is also absorbed, lost by absorbing with some materials. So this gamma particle is having a chance, to interact with matter, because gamma particles are no charge particles. So when a beam of radiation that's penetrating through a matter, that is absorbed completely. So here some processes are happening. So the important process, the physics people, the physics faculty, the three important properties of this interaction with matter are through this photoelectric effect, Compton effect, and pair production. Now, what is photoelectric effect? So the photoelectric effect is when a photons hit this atom. When a photons hit an atom, what happens? It is some electrons are moved from this atom. So when a photon collides with an atom, it may impinge upon an orbital electron and transfer all of its energy to the electron. So the photon, when it hits an atom, what happens? It hits this outermost electron. So the electron gains its whole energy, and the electron starts moving from the atom. So this atom now becomes ion. Hope you understood. So this when an atom loses an electron, what happens? This atom now becomes ion. So this property is called as photoelectric effect. So this phenomenon is called as photoelectric effect. So here, how the condition here is, when an incident photon is, the photon's energy, we will write it as h nu. H is the Planck's constant, nu is the frequency of this gamma rays. So this h nu exceeds the electronic binding energy, because all electrons are binded with this atom with a binding energy. So this h nu exceeds the binding energy. The kinetic energy of this electron is what? H nu minus EB. So EB, h nu is the energy of this photons. So this energy is given to separate an electron from the atom. So the separation energy is nothing but the binding energy. So it lost little energy to separate out this electron. So the electron is the separated electron is moving with an energy that is h nu minus EB. So this phenomenon is known as photoelectric effect. So the next interaction method is Compton scattering. As an energy of photon approaches 0.5 million electron volts, the greater tendency for the interaction electron is, that is a Compton process. So here the Compton process is, so the photons is coming, this is hitting this electron. So when it hits an electron, what happens? The electron is recoiled in one direction with an angle phi. And this electron is the photon is scattered in one direction with making an angle theta. So the photon of energy h nu strikes a free electron, the photon with energy h nu prime, because it is losing some energy when it hits no. So the scattered electron is moving with an energy h nu prime and scattered with an angle theta. And the electron is recoiling by making an angle phi. So here we can say this del lambda equal to lambda prime minus lambda. So this lambda prime is nothing but the wavelength of the scattered photon. That is equal to h by mec into 1 minus cos theta. Now the next interaction method is pair production. So the pair production is, so here we are losing is gamma. So the pair production is nothing but the gamma particles or the photons are interacting with the nucleus. Now, as a result of this interaction, what happened is the photons are disappearing, but a positive positron and an electron are generating. Okay, there's a birth of positron and electron by these photons. So this is called as electron-positron pair. So this, although the nucleus does not undergo any change, here the nucleus is not undergoing any change. So when this photon is hitting a nucleus, what happens? For positron, that is E plus, and then electrons are created. So this, you know, the E plus, the combination of E plus and E minus, we call it as a pair. So a pair is produced. A pair is produced. A negative charge and a positive charge, a pair is produced. So the gamma ray will not dissipate in empty space by producing this electron-positron pair. Now, this is a combined effect of interaction of gamma rays with matter. You see? So here this gamma rays are coming. That is the energy is starting from 0.01 million electron volt. Now what happens? So in this lower region, the photoelectric effect is dominant. Because we don't know, because these three processes are related with the energy of this photon. So with the energy of the photon is less than 0.5 million electron volt, the photoelectric effect is dominant. And if the energy is between some 0.5 and 10 million electron volt, surely the Compton effect dominates. And beyond this, hello? 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 Hello?
Ma'am, yes, ma'am.
Is what is some noise coming? Nothing happened?
No, ma'am, no, ma'am.
Everything okay?
Yes, ma'am, yes, ma'am, sir.
So you're the participants. I'm getting an answer from participants or the organizers? Participants.
No, ma'am, from organization.
Participants. Okay, nice. Am I clear to you all?
Yes, ma'am, yes, ma'am.
Very good, very good. Okay, so this diagram is very important as far as the interaction of matter, interaction of gamma rays with matter is concerned, because we all know this pair production. We all know the incidents or the interactions, but we should be very careful in these three by understanding this diagram, the combined effect of this three processes, that is the combined effect of interaction of gamma rays with matter. So here we can see this the less than 5 million electron volt, which is dominant. The photoelectric effect is dominant, and between this 5.5 and 10 million electron volt, the Compton effect is dominating. That should happen. So if the gamma rays are coming with the energy 1 million electron volt, nothing, photoelectric effect will not happen. Pair production will not happen. What will happen? Compton effect only happens. Now the energy is beyond 10 million electron volt. Compton effect or pair production, the photoelectric effect will not happen. What happens? The pair production will happen. So this is very important, this interaction of gamma rays with matter. Now, actually, this the topic, the ATAL topic, your FDP program. Actually, it is the radiation exposure and its impact on human health. So I thought I should include few slides related to this human health. I'm not going into this biological view and all, since you know I am a physicist. I cannot say much about your biology or your medicine, anything, but the interaction of radiation I should mention. So I am mentioning a few interactions with the biological matter. Am I okay? Am I okay? Am I okay with discussing this interaction of radiation with biological matter?
Yes, madam. You're
Yeah,
you're
because
okay with you.
actually in the coming sessions, the experts will give a very good the talk in the biological matter and all. But
Yeah.
participants, participants, please mute your audio. Participant, please mute your audio, please. Yeah. So now we are taking this out. Now we are so far we have seen this three important interactions. Now we are just touching few the interactions of radiation with biological matter. So when the radiation passes through a body, it loses its energy by interacting with the atoms. I know. I told you, okay, no? So when the radiation hits this when it passing through the medium, it is hitting with the atom or hitting with the nucleus. Okay, whatever is happening. So here what happened is when the radiation is hitting with the body or the biological cell, it also do some interaction with body cells. That is there. So there is two mechanisms. So we call this two mechanism is direct and indirect effect. So the directly ionizing particles are charged and they produces ionization at a short interval of time. So this when a particle is hitting, so what happens immediately? Sometimes immediately some ionizations happens. So ionization means what happens when it hits our body cells. The body cells has some atoms or something, so the neutral things. So that is interacting, some ionization will happen. So that is direct ionization, direct effects. And the indirect effects is indirectly ionizing particles can penetrate deeper into the tissues before interacting by producing by the production of directly charged particles, within causing further damage. Okay, so this indirectly means, so directly means immediately it hits the cell, it ionizes our body cells. But indirectly, it will not immediately it won't ionize, but it goes through it travels more distance. Okay, but after going through, it also surely it creates some damage in the cell. So when a radiation interacts with water, so this is a good example of this indirect the effect. See, when a radiation interacts with water, it is for the example for the chemistry faculty. So when a radiation interacts with water, it may break the bond. It can break the bond, and there's a what happens? The water molecules, you know, that's H2O. The H2O is the fragments are created. That is hydrogen H and hydroxyl OH. Okay, H and it split it into H and OH. So these fragments may recombine, because in H2O, what happens? It is not H2O molecule that is splitted into H and hydroxyl, hydrogen and hydroxyls. So these fragments may recombine in a lot of ways. So one way is it can combine as hydrogen peroxide also, because you have a lot of H and you have a lot of OH. So that can create what happens. So two hydroxyls, I don't know what's the actually chemical reactions and all. So here what happens? Some hydrogen peroxide may also form. So that would also the destruction. Actually, that this H2O2 hydrogen peroxide is it surely destructs this. Now the biological effects of radiation. The human body contains different types of cells, and the sensitivity varies considerably according to their rate of reproduction. So the rate of reproduction. So if the radiation hits in this body, what happens? It damages, and immediately some cases the reproduction will be greater, but in some cases it will not regenerate. So here we can say the blood cells, constantly regenerating cells, which produce blood, are the most sensitive, because the sensitive is the blood is more sensitive. Now the human body. So human body have a tremendous ability to repair damage. So in many instances, the cells are able to completely repair all damages and function normally, because we are all exposed to radiations. But in few people, but many people, but I cannot say few or many, but few people, they are exposed to radiation and they are getting diseases. Okay, so but sometimes the lucky people, even if it is getting some damage, that the ability to repair the damage also. So in some cases, the damage will be sufficient for cell death. So the other possible result of radiation exposure is that the cell is affected in such a way that it does not die, but it's simply mutated. The mutated cell reproduces and thus perpetuates the mutation. This could be the beginning of malignant tumor. So it is not the radiation is not a very it is a very serious thing. So if you are exposed more radiations, what happens? We'll get the cell will get permanent damage or the mutation, and we'll get ill effects also. So here the acute radiation syndromes. So the biological effects of radiations are typically divided into two categories. The first consists of exposure to high doses of radiation over a short period of time. So very short period of time, you are getting a very high dose. So that is one type of exposure. And the second type of exposure is exposure to low doses for a long period of time. So in sometimes for a 1 month, 1 day, we are exposing a huge dose. So that is the radiation effect. So the radiation effect is one type. And another one type, we are exposed to the radiation for a longer period of time. Okay, so that is also producing some chronic or long-term effects. And the sensitivity of various organs of the human body correlate with the relative sensitivity of the cells, which can be composed. So therefore, the rapidly dividing tumor cells are also highly sensitive for the radiation. So the whole body, the responses. So the cause for this. So the cause a rapid. The whole response to this body, that is called as acute radiation syndrome, that is ARS. So therefore, this acute radiation syndrome, that is ARS. So the linear non-threshold hypothesis is accepted by ICRP for this the as low as reasonable achievable. So this ICRP is the International Commission of Radiological Protection. They have given some the parameters for this the dose limits. So ICRP is an International Commission on Radiological Protection, ICRP. So this ICRP given like this, the effective dose for this occupational workers. So occupational workers are the people, they are working in this nuclear reactors, some nuclear laboratories and all. So they can have the maximum limit of the dose is 20 millisievert per year. But actually this dose, the effective dose for the general public is only 1 millisievert per year. And then for this occupational workers, the average dose is 5 years. For the whole 5 years, they can expose, the effective dose should be of 100 millisievert is in whole 5 years. But the condition is it should not exceed 50 millisievert in a single year. So the 50 millisievert, so 100 millisievert in 5 years, but it should not exceed 50 millisievert in a single year, because all the occupational workers are well monitored, and all the occupational workers are given some there's what is called some badges and all. So that is this dose is always counting. Okay, the TLDs and all are given to those workers. So immediately, periodically, their dose, the effective dose is checked for this occupational workers. So this the nuclear reactors, everybody, the organizers, everybody, they are giving full protection to this occupational workers. And the annual effective dose for the lens of the eye, so that's also they are checking. So that is should not exceed 150 millisievert, and for the skin it should not exceed 500 millisievert per year. And for the effective dose for the public, for us, that is 1 millisievert per year, and that is 15 millisievert per year for the lens of this eye, and 50 millisievert to the skin. So this is the ICRP dose limits. Hope you understood this. Hello, sir. Shall we start?
Yes, ma'am. Yes, ma'am.
Yes. Yeah. Hope all the participants have arrived.
Ma'am.
Yeah. Okay. So far we have discussing about the interaction of radiation with matter. Now we are going to see why to detect radiation. So that is the question, that why to detect radiation. So the reason is for the environmental safety, we have to detect radiation, because as far as this in your this keynote address, sir said the radiation is everywhere, and in few places the radiation is very high. So this high radiation places are called as high background radiation area. So it is a very that is practically we should survey this environment for radiation safety. So that's environmental safety is very important. So we have to detect radiation. And for the personal protection and occupational workers. So the people, they are working in this nuclear reactors and nuclear laboratories. So the occupational workers also, they have to detect this radiation, how much radiation they have exposed. So for that, we have to detect radiation. And from the medical field and all, we have to calibrate some instruments. And for the power regulations in nuclear reactors, we have to detect the radiation. And for the research applications also, we have the radiation detection is necessary. Now we have to the next is for the medical field. The radiation dose is also important for all the radiation, the nuclear therapies and all. The exposure for this X-rays, people, they are taking these X-rays always. They're taking a lot of diagnosing things. We are exposed some radiations, and the medical field also, the diagnosis and this is radiation is important, and the food radiation. For preservation of this food, the radiation is important. So we have to detect for the preservation also, we have to give a little some other limited radiation so that the food will stay for a long time. Now, how to detect radiation? So that is very important. Now the topic, this session's topic is interaction and detection of radiation. So far we have seen the interaction. Now we are going to see how to detect radiation. So the radiation, so I'm staying in a place, actually my place, I'm living in Kanyakumari district. So my place is a high background radiation area. So since I'm staying in this high background radiation area, I cannot see the radiation. So nobody can see, nobody can hear, nobody can feel, or nobody can smell or taste. Okay, so we cannot there's a taste or smell, we cannot sense the radiation. So we have to detect it properly. So we have to detect and measure this radiation by using some instruments. So all work in the people, and all work on the principle of radiation ionizations. So the ionization principle, and the radiation detectors are also called as radiation sensors. They are these instruments, they sense and measure radiation emissions or levels of radiation produced by the source. Now the radiation units. So when we have to measure this radiation, we should understand the units of radiation. So the radiation effect is measured in terms of exposure or dose. So exposure is defined as a charge released per unit mass. So how much charge is released per mass is called nothing but an exposure, the radiation exposure. Now the dose is defined as how much the radiation we have exposed, we have received, absorbed. That is the energy absorbed per unit mass. And the unit of exposure dose for X-rays or gamma rays is called as Röntgen. And the absorbed dose unit is Gray. So that is 200 rad. Now another thing, the REM is a unit of radiation dose or health effect of radiation. So that is REM is nothing but Röntgen equivalent man. REM. The REM is also a dose, radiation dose unit. Now the sievert is the unit of the stochastic health effect of ionizing radiation, and that SI unit of dose equivalent is sievert. And also the effective dose unit is millisievert. So these are few units. I think this is not for you, this is not applicable to you, but this is for the scientists and the laboratory workers. They have to they keep these units in their mind. Then the effects of radiation on detector. Let me go fast in the slide. Sir, Krishnamurthy sir. Hello. Yeah, because my time is very limited. So I'll go fast and discuss this detectors. Okay, sir?
Yes, madam. You can proceed till 9:15, madam. Later on, you can go for the interaction.
9:15. Okay, even 9:15. I have only 1 hour, sir. So
Yes,
I think
madam.
I will go a little fast. Okay, sir?
Sure, madam.
So I'll skip few slides. Okay.
Okay, fine, madam.
Yeah.
Okay, madam.
So now we are coming to the detectors. So the few detectors. So you all hear about these detectors. The function of the detector is to produce signal for every particle to enter in it. So this the function of the detector is to produce signals. Okay. So every detector once works by using some interaction of particle with matter, and the detectors are of following types. They can be categorized into the detectors of variety. The first important detector is gas-filled detector. So the gas-filled detector is also categorized. There are 3 types of gas-filled detectors. There's first one is ionization detector, proportional counter, and Geiger-Müller counter. And the second type of detector is scintillation detector. And the third one is semiconductor detector. So these 3 are the very important detectors that the scientists we are using, or the laboratories we are using this in our local people. But there are other type of detectors also, that is spark chambers, bubble chambers, photographic emulsion, and thermoluminescent dosimeter. So now in this session, we are going to discuss the first 3 types: gas-filled detectors, scintillation detectors, semiconductor detectors. Altogether, actually, the gas-filled detectors, we are going to see this ionization, proportional, and Geiger-Müller, then scintillation and semiconductor detectors. Okay. Now, this the criteria to evaluate the performance of the detector. So this every instrument, if you choose an instrument, the instrument should have some importance. So here we have to say some sensitivity. So the first criteria to choose an instrument is the instrument should be more sensitive. Now the instrument should be high resolution, energy resolution. Resolution should be good, and the time resolution of the detector is its pulse resolving time, and the detector should have good efficiency. So the first one is it is sensitivity, and it should have a good energy resolution, and it should have a capability to pulse resolving time. And the fourth one is it should have a detector. The detector should have a great detector efficiency. So these are the criteria for the good performance of a detector. Participants, am I clear to you? Participants? I think they didn't come back from the dining hall. Participants? Hello, participants.
Ma'am, we are hearing, ma'am, mostly.
Hearing. Okay. Hope you all finished your dinner. Okay, now we are going first. This is the criteria to evaluate the performance of the detector type. So that there are 4 important performances. We have to keep it in mind. What is first one? Sensitivity, energy resolution, then time resolution, and the detector efficiency. Now, the commonly used detectors in the laboratory, so as I told you, they are gas-filled, scintillator, and semiconductor detectors. Now, in these gas-filled detectors, when the radiation interacts with matter, it always produces ionization. So a common method of measuring radiation is to collect the ions it produces in a gas. So the more ions we collect, more radiations we have. So the gas-filled counters with sufficiently high applied voltage, a secondary electron is produced and causes further ionization. So there are 3 the types of instruments that operates along this line is our ionization chamber, proportional counters, and Geiger-Müller counter. So all these, the important principle is what? It when they interact, the radiation is interact with matter and they produce ionization. So here in this gas-filled detectors, ionization chamber, proportional counters, and Geiger-Müller counter. So this ionization chamber. So the interaction of charged particle with gas leads to an ionized and excited molecules along the path. So if a particle, if a radiation is entering into this detector, what happens? So it is making an interaction with the gas molecules, the gas particles inside this chambers, and it is ionizing this excited molecules and on the way. So wherever it is going, it is making an ions. So the important information is the total number of electron ion pairs created along track on the radiation. So when a free electron meets a gas that attaches electrons easily and a negative ion is formed. So a free electron meets a gas molecules, what happens? So the gas molecule now becomes a positive, that becomes an ion, or that is called as negative ion. So the oxygen is a good example. So when a free electron is diffusing in the air, it's converted into negative ions. But in contrast, nitrogen and hydrogen and noble gases, they won't make any, the electron will not attach. So the electron continuously migrates. So electron will not, because when on the way, when this electron is passing and hitting this nitrogen or hydrogen or noble gases, it will not lose this electron. So electron further migrate from place to place. Now the instrumentation of this ionization chamber. The chamber is normally a sealed cylindrical. This left-hand side. Can you see the two diagrams? The left-hand side, you can see the diagram. The first is the diagram is a cylindrical chamber. That is the sealed cylindrical arrangement. Two electrodes are electrically insulated from each other, and the battery is connected across the chamber. That makes the electrode positive. Electrode positive. That is the center. And the outer cylindrical this body is the cathode. So that is negative, and the anode is positive, the center. Now the battery is connected across the chamber, and the entire where electrode positive and outer cylindrical electrode becomes negative. And if the voltage is high enough, we can collect the ions that produces in the gas. So here, this is a graph showing the voltage increases, the number of ion pairs also increase. So the voltage increases, ion pairs also increases. Now the ionization current. So here, to collect electron ion pairs produced in the gas filled detector, an electric field must be applied. So if the electric field inside the detector is strong enough, that recombines becomes negligible. So all the charges are effectively collected without loss. So if you give more voltages, what happens? When you give more voltages, the electrons will be easily goes through this chamber. So that's called this the ionization, the ion saturation region. That's ion saturation region. So that's the middle, the plateau we are getting. That is the constant. So this region is called the ionization current. That is the ionization current is from the x-axis to this the blue line. Okay, so that is the saturation current. So the ionization current. Now in this ionization chamber, the next diagram shows imagine that radiation has produced several ion pairs in a volume of gas between two metal plates. So the electrons and positively charged ions will drift and eventually recombine until there are no ion pairs left. So if we made one plate positive and another plate negative, then the electrons will be attracted to the positive electron, and the positive ions will be collected to this negative cathode. A negative electrode, that is cathode. So will we collect all the ion pairs in the electrode? So that's the question. So will we collect? So because the ion pairs are forming, so the electrons are moving, or the beta particles or the gamma particles, they are moving. What happens? Will we collect all the ion pairs collected in the electron? So that's a question. So actually that depends on the battery. If the voltage is low, what happens? The attractive force is small, and many ions will recombine because the battery charge is very less. What happens? So the attraction power is less. Whatever. So on the way, the electron is moving very slowly. So on the way, when it meet a positive ion, the electron will recombine with this and becomes an atom. So if the battery power is very high, if the battery power is very high, when we increase, we will collect more and more the ions. We can collect more and more ions. So before recombining, it will be drift towards this positive or negative electrode. The next way we are going to see this ionization chamber, the limitations of the ionization chamber. Ion chambers are feasible for pulse mode operation. So the pulse mode operation we'll see in the later sessions also. So it is least feasible for the pulse mode operation, and the signal amplitude is extremely small. In the ionization chamber, the signal amplitude is extremely small, and the gamma rays deposit a significantly lower amount of energy to the detector. So these are the limitations. And the incident radiation is fast electron or gamma ray, then the pulse amplifier is even smaller. So here, if there's a radiation is incident is a gamma rays, what happens? Because the radiation, the gamma rays, as you know, it has no charge. So the amplitude is the pulse amplitude will becomes, because the ionization power is very much lesser than beta and alpha, because gamma's ionization power is gamma's ionization power is 10,000 less than alpha and 100 times less than beta. So what happens? So if this is gamma particles, then the pulse will be very short. So if the initial signal amplitude can be made much bigger, the pulse processing becomes easier. So the first signal should be very greater. The next, so this much about the ionization chamber. So the next gas-filled detector comes is proportional counter. So the proportional counter is also this, the principle is same as the ionization chamber, but the output is proportionally increased. So the proportional counter, the applied voltage is kept constant, but the final number of electrons collected by the anode will be much more than, but proportional to the original number. So just like the electronic circuit, the feedback is given like this. So here the output is proportionally increased with respect to this input supply. So an ion chamber will produce a current that is proportional to the number of electrons collected each second. So the proportional counters amplifies this ion, the current, ionization, the individual burst of ionization, so that each ionizing event is detected separately. So therefore, the number of ionizing events, whereas ion chambers measure almost the ionization produced by all the events. So the proportional counters can be designed for all type of radiation. So in the proportional counter, the working is just like the ionization counter, but the output is proportionally with respect to this input. So the next is the drawback of proportional counter. The main drawback of proportional counter is actually the proportional counter is a portable instrument, but it requires very stable power supply to amplify this input sections and all, amplify so this is difficult to provide a portable instrument. So that's why the proportional counters is fixed in a laboratory. So it cannot taken outside for an environmental survey or for this, it cannot be used as a portable instrument. Now the proportional counters work or operates at a higher voltage than ionizing chamber. So the initial electrons produced in ionization, ions are accelerate with enough speed to cause additional ionizations. And the gas multiplication. So in this gas multiplications also, the gas multiplication is induced by strong electric field. So the gas multiplication is induced by strong electric field. Am I clear to you all? Hello, all participants?
Yes,
Hello,
you're audible, madam. You're audible.
Am I clear to you?
Yes,
Can you
madam.
Can you understand? Can you understand? Could you understand all these sessions I'm taking?
Participants can respond.
Okay. Yeah, please participate. Yeah, Arul is chemistry is giving hands. Yeah, thanks, Arul. Chemistry. We'll meet. Okay. Okay. Come on. So here this because I am skipping few slides. Because of this time limitations, I'm skipping few slides. So that's why I'm asking you. Okay. Now this gas multiplication is induced by strong applied electric field. Now after creation of this radiation interaction, both electrons and ions make many collisions with neutral gas molecules until they collected. So on the way, this is because this proportional counter comes under this gas filled counters. So this proportional counters also there is a gas. So this is the process is repeating till it reaches this output. So when an electric field is strong enough, the electrons get high kinetic energies between collisions and eventually can ionize neutral molecules also. So when the speed of this photons are greater, there's a tendency to collide with this neutral molecules. So ions have no mobility and they attain very little energy between collisions. So ions have no low mobility. Why we can say ions have no low mobility? Because the ions are nothing but the charged atoms. So atoms are very bigger when comparing with the photons. So atoms will be there, it will be immobile. Okay, so the ions have low mobility and they attain very little energy between collisions. Now, this is the design of this proportional counter. So this proportional counter is also this just like your ionization chamber. You have the cylindrical system. So the negative ion is given to the cylinder and the anode is connected to the positive. Now this left-hand side, it is given some electronic design for the proportional counter. This proportional counter is in the left-hand side is proportional counter. Now the preamplifier. Now this is scalars. High power supply is given there. Now electron collection versus voltage. So this is a graph. Can you see the graph in the right-hand side of the slide? Can you see? Is it visible? The right-hand side graph, is it visible to you?
Yes, ma'am.
Yes. So in this, so here we are going to see the electron versus the electron collection versus voltage, or the voltage versus electron. So we are drawing this plotting this anode voltage and the electrons collected in this x-axis. So we are just comparing now the ionization chamber and the proportional region. Ionization region and the proportional region. So from this graph, you can understand in this ionization chamber, we told you the ionization chamber, the incident particles are, incident rays is just like the uncharged particles, the output will be very lesser. Is it right? So just like here, you see, this graph depicts the same. So the anode voltage is lesser, that is some 200 volt. What happens in the ionization chamber? The electrons collected is 10 power 2, that is 100. That's 100. But when it is here, that is nearly 600. That is 600. Can you see this? The 600. Can you see the graph? Participants, can you see the anode voltage 600?
Yeah, yes,
madam.
Can you see the full graph? Can you see the full graph? 600, yeah. So in the 600, you see the proportional region. Yeah.
Yes,
the proportional counter, what happens? The proportional counter, when it is increasing, what happens? So for this, the ionization chamber, 200, so you are getting some 110 power 2, that is 100 electrons. But in this proportional counter, we can increase further voltage. So that is, we can increase the voltage up to 600 voltage. Now the electron producers will be 10 power 4 electrons. That is 10,000. So in this ionization chamber, we can collect 100, but here we can collect 10,000, 10 power 4 electrons. So this proportional counter, the pulse will be very high. So the number of electrons collected will be very high. So this let us assume that the beta particles ionize the gas in detector to produce 100 primary ion pairs. It will be collected to the anode. So that is voltage and the electrodes is high enough to collect all the electrons before they have chance to recombine. So we should be very careful in these detectors. The applied voltage should be very high before making this ion electron or ion and electron combination. When it combines, what happens? The charge will collapse. So there is no charge particles. So if it is charged, we can detect it. So the primary electrons are accelerated to the rush to the anode. So such an extent that they themselves produce further ionization. So the sufficiently high applied voltage, the secondary electrons produce on the way, they can make further ionization. So the effect of this is called gas amplification. The gas get amplified, the ions get amplified. So first two counters we saw, the ionization chamber. Now we saw the proportional counter. Now we are coming to this Geiger counter. So this Geiger counter is very famous in our laboratories. So Geiger counter, everybody will say this GM counter. We won't say this Geiger counter, we say it as a GM counter. So the GM counter is it delivers a pulse at each time the particle produces an ionization at the detector. Actually, this Geiger-Müller counter, the output is collected with the mechanical count. Just we'll hear some tick tick sounds. Okay, so but that is also measured using your the electronic devices and all. The signals will be counted. So this the Geiger counter is to detect beta radiation as well as gamma radiations, because the detector tube must have a wall thin enough to allow beta particles to penetrate it. So such tubes are called thin-walled tubes, and they're often used for this portable contamination meters. So the GM counter is used in this portable meters and all. Now this is the schematic diagram of this GM counters. The same is similar for us. Ionization chamber, proportional counters, and this GM counter, the principle, everything is same. Okay, so here also we are filled with this noble gases. So the GM counter is the instrument used to measure the ionizing radiation using the ionization effect, and it is one of the world's best known radiation detection measurements. GM counter consists of cylindrical metal tube whose wall is a cathode and the coaxial tungsten wire is an anode. The tube contains argon or neon at low pressure, and the electrodes are kept in a container provided a thin mica window. So through this thin mica window, the particles, actually the source is given, and the rays are emitting, and that is allowed to pass through this thin windows. Now, the power supplies of 1000 volt is connected. The output goes to the pulse amplifier, and the pulse can be counted using mechanical counter. So count can be scaled down using a scalar circuit. So the counter has a meter marked counts per second. So actually the counter, that the rate meter. So in this Geiger-Müller counter, the rate meter is there. So that is count per second. So how much counts? So when we use the people, those who did the work on nuclear there's a research in this radiation field, you all know we must have did the work in beta counter. These are the Geiger-Müller counter. So here we'll see this count per second or disintegration per minute, DPM, or count per second. So this count per second is we will count, actually this is mechanical count. So that is counted by using this rate meter. The rate meter, the unit is counts per second. So here, actually in here, usually we have a loudspeaker, so we can hear this click, click, tick, tick sound also we can hear. For the quantitative work, 6 scalar is made more accurate. Now, actually, I told you in this Geiger-Müller counter, this is Geiger-Müller counter is one of the gas-filled counters. So this here, the gas-filled is ideal gas, that is argon, or argon is noble gases is inert gas is filled with. So this ideal gas is filled in this Geiger-Müller tube. So the ideal gas would be inert and abundant, and it is heavy. So these are the properties of this ideal gas. Ideal gas or inert gas. They are very abundant in nature, and they're also very heavy. So argon in air is so it is abundant. And noble gas, it is inert. So argon is heavy, which allows for no deposition of energy within the gas. So it will not deposit. So this increases the detector's efficiency. So the argon is heavy, which allows for more deposit. So it allows more energy deposition. So what happens? So because it deposits more energy, so the detector efficiency increases. So this GM counter is generally used for detecting gamma or beta radiations. So now the detector concept I'm skipping. Then who designed this GM counter? So actually GM is Geiger-Müller. So the Geiger counter is named after this Hans Geiger, a German scientist, actually who have been working for this construction of this counters from early 1900s. But successfully, this Hans Geiger and W. Müller, who both they invented in 1920s. Now here there's a principally same as your ionization and proportional counter. That is, charged particles ionize the gas through which they pass. Electrons are producing during the ionization get accelerated under high potential and produce further ionization. So here we can see this, the amount of, actually the electron volt. Electron volt is an amount of energy that an electron would gain when passing through a potential difference of 1 volt. So when it passes through 1 volt, 1 electron volt amount of energy that the electron would gain when passing through a potential difference of 1 volt, that you keep it in mind. So here in this Geiger-Müller counters, in this gas ionization counter, 1 electron volt is the amount of energy that electron would gain when passing through a potential difference of 1 volt. Okay. Now, when a charged particle or ionization particle is passing through a gas, it collides with molecules. And often an electron may be driven away from the molecule and they're said to be ionized. And the electrons are rapidly accelerated towards the anode and the potential due to the potential difference between these electrodes. Now we'll go to this. So this is the Geiger-Müller counter. The types of radiations detected by this Geiger-Müller counter. The gas-filled thin-walled Geiger-Müller counter will detect beta particles much more effectively than gamma photons, because gamma rays will go through this tube without interaction. So as a general rule, you can say that Geiger tube will give a pulse for every beta particle entering it. Geiger tube will give a pulse for every beta particle that is entering it, but only we can see 1% of gamma photons passing through it. So, but we can see, because gamma particles also going, but you know that the property of the gamma particle is it is penetrating through a medium, so it can move through a thick wall and all. So the gamma particles are penetrating without touching the detector, but the beta particle is, if it is going through the detector, all the beta particles will be detected by this Geiger-Müller counter. So normally the Geiger-Müller counter is good for counting these beta particles. Why not for alpha means? Because when the alpha particles, you know, the penetrating power of the alpha particle is very less because it has a very high ionization tendency. So when alpha particles also should enter, what happens? Laser, when it travels, it will be ionized and it loses its nucleus simple and it becomes an atom. So it will not, furthermore, it is an alpha particle, it becomes a helium atom. Okay, so this Geiger-Müller is good for counting beta particles. Next, we'll see the characteristic curve for this GM counter. Characteristic curve for this GM counter. So in this GM counter, see, in this GM counter, you know this, as in the beginning, I told you in the GM counter, the electric voltage, the voltage applied, or the threshold voltage, not the threshold voltage, the voltage. Actually, the GM counter operates with a voltage of 1000 volts. So the x-axis, you see, the x-axis, it starts with 1000 volts. Now in the y-axis, you can see the count per minute. So it starts, the Geiger-Müller count operates from 1000 volt. So this the count is started. The count is started. Now it reaches a threshold voltage because the number of particles collected is increasing. It is exponentially, it is increasing. It is steeply, it is increasing. Then after reaching a particular voltage, there is a plateau region you are seeing. See, the number of particles remains almost constant. So this region we can call it as a plateau region for the operating region. Okay, so this is very important for this GM counter. So the GM counter remains more or less constant for a range of applied voltages. This region of constancy of count is called as plateau region. So the Geiger counter is characterized by so-called plateau curve. So in this curve, the counting rate of a given counter is plotted as a function of voltage. Now, here, actually, in this GM counter, the important matter happens here means the Geiger counter, on the way of its process, the detector is paralyzed for some time. The detector is paralyzed for some time. It will not, the electrons or ions are not moving, so it is paralyzed for some time. So that time we call it as a dead time. that we call it as a dead time. So that is the word is very important for the Geiger-Müller counter. So this Geiger-Müller counter is the time interval of which the counter completely insensitive to your incoming particles. That is insensitive. The particles will come, but it will be insensitive. It will not counter anything. So that is called as dead time of GM counter. So that is why is the electrons produced by the ionization event are quickly accelerated to the anode, but it takes longer time for remaining positive ions to reach the cathode, that is trundle off to the cathode, and the detector is paralyzed until they are out of the way. So this is called as dead time. This is called as, so the reason for the dead time is under normal operation of GM counter, the total number of ion pairs formed per incident radiation is very large, and the electrons are collected by the anode very fast. On the other hand, the positive ions become that if the ions, because of the larger mass, it takes a longer time to reach this cathode. So thus, there's a dense positive charges all around the anode. So the dense positive charges all around the anode. So it is taking a long time to reach. So all will be crowded in a place. So this efficiency shields the anode from applied voltage. So okay. So this is the denser particles will shield this anode from this applied voltage. So if another radiation is incident within the active volume of the detector, it does give rise to ionization and gas amplification. So, but the pulse amplitude will be below the detection limit. So since the effective anode potential is below the threshold voltage. So the reason is, so once again, I'm explaining the reason. So as the positive ions are collected to the cathode, the effective potential increases until finally it exceeds the threshold voltage. Now it is back into operating condition, and subsequent radiations will be able to register this measurable output pulse. So until the positive ions are reached the surface of the cathode tube, the next particle will not be detected. So the time interval for which the counter is completely insensitive to the incoming particle is called as dead time of the GM counter. So any instrument which has dead time is its efficiency or the sensitivity decreases. So because when you're using this the instrument, on the way it is not functioning for a time. So that means the efficiency decreases. So this parameter is called as dead time. So that is why that's a very major disadvantage of this Geiger-Müller counter. Now this quenching in this GM counter. So here, how to quench this, how to overcome this dead time. So the existence of dead time results in loss of counts. So dead time means, so it is the counter is dead for some time. So the radiation is going on. So the instrument is not it is not working properly. It is because it is unable to count unable to count the radiation counts. So thus it is desirable that positive ion sheath is formed around the anode wire. So for the quenching of this to overcome this dead time, it is desired that a positive ion sheath is formed around this anode wire. So the process of eliminating undesired positive ions sheath around the central anode wire is called as quenching. So many methods have been used for quenching, but most accepted method is self-quenching method. So the self-quenching method, is the quenching process is the tube deionizing after the particle has been detected. So the faster the tube can revert the non-ionized state. So here, the faster the halogen like iodine are often added to the gas, the gas to improve this quenching action. So what happens? The quenching action. So this quenching the non-ionized state. The elements like halogens. The halogens are included for this self-quenching of this GM self-quenching against this dead time. So the dead time will be reduced. Now here we have so in the previous graph we saw there's the relation connecting this ionization chamber in the proportional region. Now we are connecting this Geiger region also. So here in this ionization chamber, the applied voltage is 200 volt, and the proportional counter it is 600 volt, and the Geiger counter it is 1000 volt. So the number of particles collected is also proportionally increased. So the ionization chamber we have collected, actually this graph little problem is there. Actually here it is 10 power, actually we saw it is 10 power 2. Yeah, no, yeah, it is a graph, it is correct. So this is graph, you see the graph, the line, see. So in this ionization rate is how much electrons are collected, 10 power 2. And the proportional region we are collecting 10 power 4. And this Geiger region is collecting 10 power 10 electrons. Okay. So this is the number of electrons collected in 3 gas-filled counters. Hello, participants. Hello, participants. Hello, participants.
Yes, ma'am.
Am I okay with you?
Yes, ma'am.
Can you catch up everything? So far we have seen, 3 types of counters. What are they? Ionization, proportional, and Geiger-Müller counter. Okay, now we are going to see this instrument efficiency. So the instrument efficiency will be increased in 2 ways. The relative position of the detector and the radiation source. So the left-hand side, you can see the graph. The first graph is, so this is a detector. So if the detector is closer with the source, the efficiency will be increased. Or we can say the detector, the size of the detector will be greater. So the efficiency will be increased. So these are the 2 ways we can increase the efficiency of the detector. Now, so I'll skip it. Yeah. So this graph you can see this is a proportional region. See the proportional region, you see the graph. So the proportional region is applied to the applied voltage. So here you see all the 3 graphs I have given to the 3 limited proportional regions. See, the first lower region is for the gamma region, the next is beta, and another one is alpha. Okay, so in this ionization chamber we can collect alpha, beta, gamma separately. So this is very important. So the ionization region we can detect alpha, beta, and gamma, and also in the proportional region also we can distinguish alpha, beta, gamma. When you see this Geiger region, the Geiger region, the alpha, beta, gamma cannot be distinguished. So you'll get a single line. So in this Geiger-Müller counter cannot distinguish all the 3 rays. So this Geiger counter will not distinguish all the 3 rays. So the next type of counter, we call it as a scintillation counter. So far we have seen the gas-filled detectors. So there we saw 3 types: ionization, proportional, and Geiger-Müller counter. Next, we are coming to this scintillation counter. So the scintillation counter, as you all know, the scintillation counter is when a particle, when a radioactive ray is falling on a substance, the tiny flashes of light produces. So that is called the scintillation process. So the scintillation process is nothing but it measures the radiation by detecting tiny flashes of light that radiation produces in certain materials. So the scintillation counters can discriminate between different types of radiation, and more importantly, even between different energies of same radiation. So there are several types of radiation counters, but the detector systems always consist of 2 components. So the first one is the scintillator, and another one is the detector. Okay, the first one is a scintillator and another one is a detector. So the scintillator is just like the scintillator is nothing but the phosphor, which emits tiny flash of light when ionizing radiation strikes on it. And the second part of this scintillation counter is detector. So that is nothing but a photomultiplier tube or phototube. Photomultiplier tube or phototube. So the scintillation counter has 2 parts. What are they? The scintillator and another one is a detector. So scintillator, normally that we call it as a phosphor. So phosphor is a material when the radiation hits on, the flashes of light are emitting. It emits the light, flashes of light. And the detector is nothing but the photomultiplier tube or phototubes. Now, what is scintillation process? The scintillation process is in which energy from certain radiation interacting with volume of sensitive material is converted into electromagnetic waves. So the frequency of the emitted electromagnetic waves is within the visible spectrum, So that can be detected. Now the sequential events took place while detecting ionizing radiation. That is, we'll see the sequence. The absorption of nuclear radiation in the scintillator resulting in excitation and ionizing with it. So when the nuclear radiation is absorbed by the scintillator, what happens when the scintillator absorbs the nuclear, the gamma or gamma radiation? The example, the gamma radiation, what happens? It is the scintillator gains energy and it is going to the excited state. And the excited state will, it will not be there in the excited state for a long time. It tries to come to this ground state. So by emitting a photon. See, all physics people, we draw the graph for the energy level diagram, energy graph. So, and a ground state, an excited state. So excited state, the time duration is very short. So it is coming to this ground state by emitting photons. That is photons. So the first one that is going to the excited state or the ionization state. The second one is conversion of energy dissipated in the scintillator to light energy through luminescent process. So that is through this luminescent process. And the transit of light photons to the photocathode and photomultiplier tube. Then the absorption of light photons at photocathode and emission of photoelectrons and subsequent electron multiplication process is happening within the photomultiplier tube. The photons are multiplied, that process is happening there. So finally, the analysis of the current pulse is furnished by the photomultiplier tube. So through some electronic equipments like electronic counter or multi-channel analyzer. So in the scintillation counter, we have this scintillator and this photomultiplier tube, and the photomultiplier tube that is just like this. It is just like the multi-channel analyzer. Now the scintillation counter. So this is the schematic representation for the scintillation counter. The block diagram. The sodium iodide. Actually, there's a scintillation material, sodium iodide thallium crystal. So this is a photomultiplier tubes, and the preamplifier is there. So we are getting this counts, and it is given to this multi-channel analyzer. So this is the exact happening. See. So this is a scintillator is given, the high energy photons are coming, it is hitting. So it is going through this. So it is focusing on this electrode. So it is passing through this. So one electron is hitting. So just focusing electrodes are there. It is reflecting back. So this to this diodes. Okay, all the diodes. So here, once again, it is coming here. The electrons are the more electrons are ejected, so the intensity increases. So finally, see the final diode, the electrons are multiplied, and the more photons are multiplied using this photomultiplier tube. So this is the scintillation counter, this counters diagram. Now, this types of scintillators, there is a organic scintillator and inorganic scintillators. Organic scintillators and inorganic scintillators. So in this inorganic scintillators, we are interested in inorganic scintillators. The inorganic scintillators we are using in this laboratory. So that is a thallium activated sodium iodide thallium detector. Okay, that is very important. Normally in our laboratory, we are using this sodium iodide thallium, NaITL, sodium iodide thallium detector. NaITL, sodium iodide thallium detector. Or we can say it as a thallium activated sodium iodide crystals used there. So here some in this sodium iodide, some thallium impurities added. So here so this is a very important instrument. That is the inorganic detector. Inorganic scintillator detector is sodium iodide thallium detector. So here the working is when an ionizing particle is passing through the scintillator material, atoms are ionized along the track. For charged particles, the track is the track is a path of particle itself. So the gamma rays, their energy is converted into energetic electrons via photoelectric effect, Compton effect, or pair production. So in any one of the ways that is interacting, and the energy is dissipated. So we have seen this the graph, the interacting sections. We saw this photoelectric effect, Compton effect, and pair production. We saw this energy. So from 0 to 0.5, we are getting this photoelectric effect. Now from 0.5 to 10 million, 1 million, 10 million, we are getting this Compton effect, and beyond that, we are getting this pair production. Okay. Now, what are the scintillating materials? Scintillators are materials that absorb energetic radiation such as gamma rays, X-rays, or neutrons that convert into short bursts of visible photons. So these photons are then converted into electrical pulses by photodetectors. Then phosphor. So there are several suitable materials. The choice depends on the type of radiation to be detected. So the cylindrical crystal, that is sodium iodide, a typical phosphor for gamma radiation. So the iodine provides most of the stopping power in sodium iodide. And when the gamma photons are stopped, the crystal, that is by photoelectric effect. And it has the lost in energy to ionize the atoms in the crystal, which produces the scintillation or light. And this is a phototube. So its function is to convert the tiny flashes of light into electrical pulses. Okay, so this is a function of this phototube is to convert the flash of light into electrical pulses. That is a function of phototube. The next is pulse height analyzer. So in this sodium iodide detectors, so we are using this detectors so that the output is very important. How to read out this the number of radiations, are the counts of the intensity of the radiation that is passed through. So that is, so here the pulse is increasing. Okay, due to this pulse, we'll discuss the pulse in this later session. So the scintillation counter, the pulse heights are proportional to the energy of gamma photons deposited in the crystal. Accordingly, if we sort these pulses in terms of their heights, we will be doing the equivalent of sorting gamma photons according to the energy. So this is called the pulse height analyzer. So the pulses, so actually how this pulses are coming, the pulses are how this gamma rays are coming. So in this when the gamma rays are coming through this the phosphor, sorry, the scintillator, what happens? So the scintillator, the gamma rays, the gamma rays are attaching. So gamma rays, that is the interaction is happening. So in this interaction, the energy coming out from the gamma rays are varies. Gamma rays varies. So it may be from a few electron volt to million electron volt, or some kilo electron volt or million electron volt. So that depends on the energy varies for each gamma rays. So that is all collected in this. That is the energy separation things are there in this multi-channel analyzer. We will see this pulses later. Okay. So here the electronic circuits is there that does that is the sorting out of this gamma photon according to their energies. So they are sorting out this gamma photons according to the energies. So energy categorizing this energy, categorize the photons according to this energy. So here the pulse height analyzer replaces a discriminator. It permits us to plot gamma energies emitted by the source by individually counting various pulse heights associated with. So the pulse height analyzer are of two types. So here the pulse heights we are going to see. So the pulse height also, there are two types of pulse height analyzer. So the first pulse height analyzer is the single channel analyzer. Okay, that's a single channel analyzer, and another one is a multi-channel analyzer. So that is that we'll see in this last session. Okay. So here we saw the scintillation counter. So scintillation counter, there are two types of scintillation counter. The one is organic scintillator and another one is inorganic scintillator. So we learned the inorganic scintillator, that is sodium iodide thallium detector. sodium iodide thallium detector. Sodium iodide thallium detector is we have seen. And in the scintillation, and another one important thing is the scintillation detector is used to measure this alpha particles. So in this, to measure the alpha particles, the scintillation detector use this for the scintillator that is used to measure this alpha particle is zinc sulfide Ag. Okay, silver. ZNS Ag. So zinc sulfide Ag is used as a scintillator to measure this alpha particle, because to measure each and every particles, the scintillator should be different. Okay, scintillation counter, scintillation, and the detector, scintillation and detector. So here the scintillation should be different. So the scintillation is ZN Ag is for what? Alpha detector, for alpha detection. Okay. Now, next we are going to that last counter, that detector, that is a semiconductor detector. So the semiconductor detector, that is also called a solid state detector. So that is the solid state detector. So solid state detector is actually, we are using in the laboratory, we are using hyperpure germanium detector, the hyperpure germanium detector. That is germanium crystal doped with lithium or high purely germanium detectors are most common type of semiconductor detectors. So the sodium iodide thallium detector is a scintillator detector, and the semiconductor detector is hyperpure germanium detector. So these both are these detectors we are using in this laboratory for measurement of this radiation the activity concentration of this radiations or the radionuclides. And the semiconductor detectors, the fundamental information carries are electron hole pairs, which are produced along the path taken by the charged particles through the detectors. So by collecting the electron hole pairs, the detector signal is formed. So here the semiconductor detectors, what happens? In the semiconductor detector, is just like it is not a scintillator. Scintillator is we are getting the light. The semiconductor detectors, what happens? So when it collides with this the particle, once again what is the ions are produced. That becomes excited state. It is coming back. So the electrons and ions are created. So the electron hole pairs are created. Now the types of different types of semiconductor detectors. The different types of semiconductor detectors are diamond detectors, germanium detectors, and cadmium detectors. And the semiconductor detectors, this is see. So the semiconductor detectors, the rays are coming. So it is creating these holes and electrons. So the germanium crystal doped with lithium and high pure germanium detectors are the most common type of semiconductor detectors. Now the next is how to choose a detector. So far we have seen all the detectors. What are they? Once again, we'll see. The first detector is gas-filled detectors. In the gas-filled detectors, we saw this ionization chamber, proportional counters, and Geiger-Müller counter. And the second type of detector we saw scintillation counter. And the third we saw semiconductor detector. Now we have to choose what type of detector we have to choose. So the choose a detector type is because we have to choose. So in this medium, we have to decide what instrument is good for for measuring the radiation with what instrument. So the source, the source and the detector we have to decide. So choose radiation detector is a particular principle of interaction. That is, we have to see this sensitivity to estimate the radiation under the detection. So here are the characteristics of radiation detectors then we can see this, we can decide which instrument can be good for the individual purposes. So here's the characteristics so that is the sensitivity of the detector, then the operating voltage. So we have only 200 voltage. So we cannot go for the Geiger-Müller counter or proportional counter. We have to go to the ionization chamber. Okay. So the operating voltage and the operating voltage region and the radiation detector range and the resolution and we have to choose a count. We have all the instruments with us. So we got to go for an instrument that has less dead time. And we have to choose this the lifetime of the instrument. So this is the way we can choose this instruments. Now the alpha scintillation counter. So alpha scintillation counter, I told on the way. So the alpha or beta particles interact with phosphor. They will also produce scintillation. So the phosphor we are using for this alpha scintillation is ZnS Ag. Now alpha or beta particles interact with phosphor. They will also produce scintillations. So the scintillation counter are described that is used to detect alpha particles as long as a very thin scintillator replaces a large sodium iodide phosphor. So normally in this gamma detections, gamma detector, we used the phosphor. What we use? We use this sodium iodide detector, sodium iodide phosphor. We use the sodium iodide phosphor. But here, if we want to use to detect alpha particle, we have to replace sodium iodide with zinc sulfide. We have to replace sodium iodide with zinc sulfide. So zinc sulfide is a phosphor for measuring alpha particle. So to allow alpha particles to penetrate zinc sulfide, a very thin mylar foil is used because we have to use the planchette type we are using. Because the source will be the sample will be a very thin, because you know the range of alpha particle is very small, very short, very small. The range of alpha particle is very small, because if you keep an alpha particle in your skin, it cannot penetrate through that skin itself. It reacts and it becomes a helium atom. So the scintillation counter, because of their low penetrating power, it cannot penetrate. Alpha particles are stopped in a scintillator and so deposit most of the energy there. And the beta will lose only small fraction of the energy in the scintillator. So the output pulse resulting from the interactions of alpha particles will be much greater than from this beta particle or gamma particle. Now, so in this scintillation counters and this semiconductor detectors, the output will be pulses. Okay, so now we are going to see the pulse heights, how to analyze the pulse height. So the pulse height, how to analyze the pulse height. So here in this pulse height, there are two types of pulse heights. The many radiation detectors produce electrical pulses whose amplitudes are proportional to the energy deposited in detector by individual interactions. So the pulse height analyzer, PHA, pulse height analyzer are electronic systems that may be used with the detectors to perform pulse height spectroscopy. Now there are two types of pulse height analyzers. They are single channel analyzer, and another one is multi-channel analyzer. So the single channel analyzer and multi-channel analyzer are two types of pulse height analyzers. So here we see, this is a very interesting thing, the pulse heights. The interesting, see, can all of you see this the thing in the screen? Can all of you see the thing in the screen, the waves? Yes. Yes, yeah. So see this the first row, it is given the analog pulses. The first row, the first column is ADC, analog to digital converter, analog to digital converter. So the pulse is coming in the analog way. That is, analog way is 1, 2, 3, 4, it is coming. Now here we have to convert it into a digital way. Okay, this ADC is given. So here the signal is going. So signal is going. So here the signal, the signal, there is no signal. So the display is, there is no display. Okay, because the analog here, the signal is no, there is no pulses. The first row, there is no pulse. See the second row, there's the first pulse is coming. The first pulse is coming. So the first pulse is coming. So the first pulse, so here the pulse is reaching here, no, one pulse. So who's the energy? So this is the energy. So actually the x-axis is given as an energy. So here the energy is corresponding to this sixth bit. Okay, the sixth bit. Not the first bit. Okay, sorry, the second bit. The 0th bit and first bit. Okay, 0th bit and first bit, I can say. So here you are getting one pulse. Here getting one pulse. And another one, the second pulse is checking for it is its pulse is in this second thing, and this the sixth one. Okay, this we can, I'll say like this. So second bit and the sixth bit. So here what happens? You are getting two pulses. We are getting two pulses. Okay. Now, actually, Yeah, actually here this should be a little bit increased. Yeah. So 1 and 1. Actually, yeah. No, sorry. I said a little wrong. So the second column, you are getting the sixth pulse. No, so the sixth pulse, there's a pulse. Now you are getting only one pulse. This is arrow. So here in this output now, the display. So the 2 peaks are there. Okay. The second bit, 1 peak, and the sixth bit, another peak. Now the third pulse, once again for the second bit. So here, what's the height? This already there is one more. So the height increases. Can you understand? Can you understand? Can you understand?
Yes, ma'am.
Yeah. So the first event, see the second column, the first event is happening in the sixth bit. So you are getting 1 pulse. And the second pulse, you are getting the event is in the second pulse, second digit, second bit. So you are getting 2 pulses, the first one and the second pulse. Now the third pulse is once again coming and collecting in the second bit. So the second bit already is 1 is there. So 1 plus 1, 2. So the pulse height increases. Now after 12 pulses have been analyzed. So once it is coming. So here you see there's a peak. So all the pulses, all the bits, 0th bit, first bit, second bit, everything is increased. So also your the 6th bit, it is increased tremendously. So it is increased. So already it got 3 pulses. So the height is 3 times that of this 1 pulse. So 3 into 1 pulse. So the height increases. Okay. So actually, so this is we are getting like this. You see the voltage output in this single channel analyzer. This is the way. The input, this is the input, and the first one is the input, and this is the second input. This is the output. So the voltage is this digital way. Voltage is digital way. Okay. Now the single channel analyzer, the another thing is the single channel analyzer is it can allow a particular voltage or particular energy to pass through. Okay, because this is using actually the single channel analyzer we are not using in the laboratory, that is using in some the reactor, some what is it called? It's not normally in the colleges and all, we are not using the single channel analyzer, we are using the multi-channel analyzer. Okay, what is the principle of the single channel analyzer is it allows energy limit. So from E to E plus delta E, energy won't be allowed. All another energy will be we are not that cannot be allowed. That cannot be. So this single channel analyzer is used to measure a particular type of sample. Particular type of sample. So that is here. So this iodine, actually to iodine, for iodine sample is measured using this single channel analyzer. So how much counts we can get from this iodine. So see the single channel, the energy is so here this energy is ranging from E and E plus delta E. So we could see that the last point, please see, we could set the level control to 350 kiloelectron volt and the width control is 30 kiloelectron volt. So that is varying from, that is 350 plus or minus 30. So that is 320 to 380 kiloelectron volt range. So this is used to find the iodine I31. Now we are going to see the multi-channel analyzer. So this multi-channel analyzer, the same thing, just like this pulses. So the energy pulses are coming, and each pulse is the energy is separated out, and this is counted. This all the energies will be separated. That separation, this is called as channels. This is called as channels. Okay, this is called as channels. So here we can see the multi-channel analyzer is an instrument used in the laboratory and field applications to analyze input signal consisting of voltage pulses. So the multi-channel analyzer, a stream of voltage pulses and sorts them into histogram. That is a pulse height. Now multi-channel analyzer sorts the pulses according to the height and the count, the number of each window give us the energy distribution. Okay, according to the energy, the pulses, the height will be increased and each will be stored in a particular storages. That is called as channels. That is multi-channel. Single channel means for a particular energy, but multi-channel means it can store as many energy is coming that is given there. So that is the multi-channel analyzer. So the multi-channel analyzer is very complex and expensive, especially if the number of channels are capable of being counted simultaneously is very large. So it operates in different modes, that is pulse height analyzer and multi-channel scaler. So this is the multi-channel. So the multi-channel means it has a lot of channels. This channel, each channel describes the energy. So single channel means it has a particular energy. That energy is E plus E to E plus delta E. So multi-channel means it has a many channels. Many energies can be seen. See, so this is a multi-channel analyzer. So the spectral analysis for this multi-channel. I'll see. Yeah. See, this is the top graph gives the output for this sodium iodide thallium detector. Sodium iodide thallium detector, and the second this peaks. The bottom one. You can get a very the sharp peaks. You can see the very sharp peaks. Okay, so this is actually this the sodium that is actually this here the what is it called the hyperpure germanium. Okay, hyperpure germanium detector. That's the bottom you can see this hyperpure germanium. Bottom you can see the hyperpure germanium. This is the sodium iodide detector. So you see, so these peaks are coming. This is for some energies are given. Okay. So here this the resolution is very high, but the resolution here is little bit lesser. Now see the resolution. The energy resolution of the spectrometer is a measure of the ability to difference between particles or photons of different energies. That is energy resolution. Energy resolution is we can differentiate the particles or photons of different energies. Now the energy resolution. So here the energy resolution, the photons. This is a photon energy. So here this is energy for here for this energy have some 50 kilo electron volt. The count is very greater. Now for this 200 kilo electron volt, there is another peak. So there are also some elements are some energy is given out from this. Some gamma rays are having this much of energy. Now here you see a big peak that is varying from 600 kilo electron volt to 700 kilo electron volt. 600 kilo electron volt to 700 kilo electron volt. Now we are going to see this the count rate effects. Now actually we have to see few the few important thing we have we are about to close the session. So before that, let me give few points. So the first one is which of the actually this the least the alpha beta gammas, the least ionizing rays are gamma is the least ionizing property because alpha beta has higher ionizing property. Now in this detectors, the energy is deposited. The radiation deposits energy in a sensitive part of the detector. So the energy is deposited in the sensitive part of this detector. Now another important thing is your photomultiplier tubes. So in the photomultiplier tubes, the number of electrons are increased. The photomultiplier tubes, the number of electrons are increased. Now another thing to remember is, now we saw this proportional region, ionization region and the Geiger-Müller region. In this Geiger-Müller region, the alpha, beta, gamma are not discriminated. That is going in one line. So we cannot distinguish alpha, beta, gamma in this Geiger-Müller counter. Now, another one is in this nuclear plant. Actually, the scintillation detectors are used to measure the tritium. So there's a nuclear plant that the detector, the tritium is used to measure this. The liquid scintillation detectors used to measure the tritium. Tritium is a radioactive material. Now, another thing to remember is, so these are the things to remember. Now we are going to have this. So in this, yeah. So actually this, so in this, I hope you understood this multi-channel analyzer. So each channel is nothing but it is it stores the pulses, or the energy is pulses. It stores the pulse according to the height, or the energy according to this height. Okay. Now we are going to see the difference between the dosimeter and the counter. So normally in the counters we are using in the laboratory, and the dosimeter also using in the laboratory, but the dosimeter measures this dose absorbed, totally the dose absorbed. So the counters measure the low level radiation such as surface contaminations, and the dosimeter is an instrument used to measure ionizing radiation. Ionizing radiation exposure, ionizing radiation exposure. So exposure is measured using this dosimeter. So the dosimeter can be of the form of a sticker, badge, that's pen type. Okay, all these, actually this dosimeter, normally the people, they are the people, they are working in this nuclear fields, they are using this radiation. I told you in this radiation units, the radiation, the radiation's exposure is normally they are monitoring periodically. Now the radiation dosimeter or a badge does not provide protection, but detects and measures the radiation that you have been exposed to. So the badge will detect high energy beta, gamma, and X-rays. So thank you so much. Thank you for your patience. So Krishnamurthy sir.
Yes, madam.
Yes, sir. Hope we successfully completed the first session. So actually the audience, the participants, now this is an interaction time. Please interact with us, with me.
Yeah. Yes, ma'am.
Actually, before that, I have to tell you, I have to share a Google form. There we have some few questions are there related the talk, and you have to fill it and send. Actually, this immediately after I stop sharing this session, I will send this to Krishnamurthy sir. Krishnamurthy sir will send to our ATAL group. Okay.
Okay, madam.
Yes, sir. I'll send to your Google form immediately after we stop sharing this. The participant, please, before you go to bed, please take some 10 or 15 minutes to complete the form and go to bed. Okay. Now you can ask questions.
Madam,
Yes, sir.
Ma'am, which type of radiation is more intense, ma'am?
More intense means alpha is more intense. That has a high ionizing power, but the alpha particle cannot penetrate through the body, because we are seeing this the biological effects and all. No, so this alpha particle, I told you in the slide, the alpha particle cannot penetrate through the body. So immediately if it touches the surface or an atom, it gets it loses its property as nucleus and it becomes an atom. So alpha particle is more intense, but it comes inside the body, it makes some harmness because the ionizing power is very high. So it creates some it ionizes. So this ionization process happens. That is called this indirect processes. The direct process and the indirect process, we saw the biological effects and all. Hope you understand. Sir?
Yes, ma'am. Thank you, ma'am. Thank you, ma'am.
Yeah.
Thank you.
Yeah. Any questions, audience?
Yeah, yes, ma'am. Yes, ma'am.
Yes. Tell me, sir.
Ma'am, is it possible to record atmospheric radiation concentration using portable device? And also, what are the low limit to
Actually,
detect
for the
using
atmosphere, yeah.
portable
Actually,
device?
the atmospheric contamination is due to this radon and thoron. Actually, we'll discuss in another session about this, the building materials and all. And that time we'll discuss more about the surface contamination and all. But that is the surface radiation is the alpha, beta, gamma is that. But the surface, we have this the radon and thoron that is also detected using this solid state detectors. Sorry, there's yeah, SSNTD. That is SSNTD. SSNTD. The detector is there to measure this radon and thoron for this surface contamination, surface environmental radiations. environmental radiations. That's it. In anything, we have the instruments to measure this radiation, sir.
Yeah, thank you, ma'am. Your session is very nice and informative, ma'am.
Thank you so much, sir. Thank you so much. You are from which college, sir?
I'm from Ishwar College of Engineering.
Oh, Ishwar College of Engineering. Yeah.
Yeah.
Sir, Krishnamurthy,
Thank
sir.
you, ma'am.
Yeah, thank you, sir. Thank you. Krishnamurthy, sir.
Participants, there are any queries, please interact with Shanti madam.
Ma'am,
Says.
ma'am, one more question, ma'am.
Yeah, sure.
Ma'am, why are we interested to detect gamma rays?
Why we are?
Interested to detect gamma rays.
Because gamma rays also has a very greater the tendency of interaction with matter, no? Because why we are interested is alpha particle cannot go and interact because its range is very less. Alpha particles range is very lesser. Beta particles range is also a little lesser comparing with gamma. But gamma can interact through environment. So it can go through our body, it can go through the food, it can go through anywhere, because I told you the gamma particle will be stopped by an intense denser materials. So when it goes through, one of the interactions may happen, photoelectric effect, or it can happen Compton, or it can happen pair production. And in this that ionizes the matter. The gamma particles can ionize the matter. So when it ionizes the matter, what happens in our in the body cells and all we discuss? So it can there's a chance of mutations and all that cells can damage. Okay, so we are much interested because since the gamma ray has longer range means the distance travel. So we are very much interested in gamma rays, not interested, but normally the gamma rays. Yeah.
Thank you.
Yeah.
Dear participants, any other questions? Okay, if there is no other questions, we can go for the concluding session.
Yes.
Information and knowledge, two currencies that have never gone out of style. We thank you, ma'am, for giving such an informative session about radiation aspects, detection methods, counters, and analysis. And I thank all the participants for sparing their precious time for making this event successful. Session 2 will be continued tomorrow at 7 p.m. And that's the end of the session. Thank you all.
So thank you so much. Thank you so much.
Thank you, ma'am.
Thank you. So Krishnamurthy sir, I'm sharing the link to you.
Okay, madam.
Yeah, please.
Yeah, I'll share to the participants.
Yeah, please share with your participants.
Sure, madam. Thank you. Thank you for the wonderful session, madam.
Thank you, sir. Thank you so much. Krishnamurthy sir, your mail ID. I got it. So I am sending through your Gmail, sir.
Okay, madam.
Yeah, please share in the ATAL group.
I'll share to the group, madam.
Yeah. So participants, please tell the participants to fill the form today itself. Because
yes,
because I have covered almost all the questions because the time limit was there. Okay, sir. So anyhow, yeah. Thank you so much, sir. I'm leaving. I'm stop sharing.
Thank you, madam. Thank you for the session, madam.
Okay. Hope you enjoyed it.
Yes, madam. Sure, madam.
Thank you so much, sir.
Thank you, thank you very much, madam. Thank you.
Yeah, because in chat also I saw, people there commented. Okay, sir.
Okay, madam. Thank you, madam.
Yes, sir.